My precious probability rules. All right, it's time for part 2 of probability rules. Let's dive right into it. Mutually exclusive events. This is a really big topic. Two outcomes are said to be mutually exclusive if they cannot occur at the same time. So we're talking about two different events. Can they occur at the same time? If they cannot, they're mutually exclusive, which we would also call disjoint. Otherwise, they're not mutually exclusive. So this matters when considering the probability of two or more outcomes occurring at the same time. Like, this definitely matters. If outcome A and outcome B cannot occur at the same time, then the probability of A and B equals 0. So this is where we now get into a world where we're talking about more than one item. And things could potentially get a little bit tricky because we're considering multiple events here. So we got to be careful that we understand we have probability of A. Right? That's the probability of event A occurring. Then we have probability of B. That's the probability another outcome B occurs. Now, if A and B are truly mutually exclusive, it means that these two outcomes cannot occur at the same time, which would tell us that the probability of A and B equals 0 because they cannot occur at the same time. Now, in statistics, we use a couple different symbols for this. Let's talk about that. So first off, we have the probability of an event A occurring. That's pretty simple. And then obviously we could add the probability of a different event B. And we could even talk about probability of a different event C, whatever. But then we talk about the word and. That means that they occur at the same time. So that's the probability of A and B. Now the symbol we use for and is this upside down U. Keep that in mind. You might see that symbol come up a lot in the AP stats course or in any stats course, but that upside down U means and. So I prefer to just write and, but I want to make sure you understand what that means. So if the A and B is 0, that means that they cannot occur at the same time. That means A and B together is impossible. That's mutually exclusive. But there are some situations where they can occur at the same time, or they're not mutually exclusive. Now, when we talk about and, we also bring in another word, which means or. And that is the probability of A or B. Now, a couple of things I want to mention here. First is the symbol for or is a U. Looks like a U. It stands for union. But that's the symbol for or. So I want you to kind of be, now I like to use the word or, but you might see that symbol, so I want you to be aware of it. But remember, the word or is a little bit confusing because you got to really think that it could mean A, could mean B. But it could also mean A and B, right? So part of the phrase A or B is A or B or both, okay? And I'm going to really try to do my best to explain that in this video, especially as we get a little bit deeper into it. But I want you to make sure you understand that the word or includes A, B, and potentially both. But let's start to look at some examples that use these words of A or B, A and B. It's really important to see these examples. So in this first one here, where we have a spinner, 7 equally sized sections labeled 1, 2, 3, 4, 5, 6, 7. If I said, hey, what's the probability of landing on a number 4 and the number 7? So this is the probability of 4 and 7. I'm going to use that symbol for and, even though I don't like it, but whatever. Now you say, wait a minute, that can't happen. That's because these are mutually exclusive events. The probability would be 0. It could land on 4, it can land on 7, it can't land on both. The spinner only has one arrow, it can't be in two places at the same time. Great example of that. But then I could say, what's the probability of landing on an even number and 5? Okay, probability of an even number and 5. Well, those would also be mutually exclusive events because if a number is even, it cannot be 5. You know, it could be 2, could be 4, could be 6, but it cannot also be 5. So once again, those are two mutually exclusive events, and the probability of that occurring would be 0 because there is not a single number out there that is at the same time both even and 5. So again, when we think about and, we think about both. Got to be both. Can't be both even and 5. All right, another example here. A jar is 20 marbles, 3 red, 7 blue, 10 green. What is the probability of selecting a red and a blue marble? So if I reach in and I select one marble, what is the probability it is red and blue? Well, a marble can be red, a marble can be blue, a marble can be green. Can't be both. So probability is going to be 0. So once again, those are mutually exclusive events because one marble cannot be both red and blue at the same time. But let's now talk about the word or. Big difference here. what is the probability of landing on the number 4 or the number 7? So now this is where 4 could make me happy, or 7, there's not my U that stands for or, 7. So I say, okay, well, wait a minute. I could be 4 or 7. So here we say, okay, well, I want to be happy. I could be happy if a 4 comes up. Well, what's the probability of rolling a 4? 1 out of 7. 7 outcomes, one of them is a 4. Or, means add, could be a 7. Well, there are 7 outcomes. One of them is a 7. Now, these two events are mutually exclusive. They cannot occur at the same time. So there is no overlap. So it's either going to be this, which is the probability of getting a 4, or it's going to be this, which is the probability of getting a 4. Add them together, I have a 2 out of 7 chance of being happy because it's 4 or 7. So if a 4 or a 7 comes up, I'm happy. So that's 2 total outcomes out of 7. They're going to now make me happy. Easy. What about the probability of getting an even number or a 5? So even or a 5. Okay, well, the probability of rolling an even number is 3 out of 7 because 2, 4, and 6 are all even, and any one of those numbers would be considered even, which would make me happy. Add the 7 outcomes. Or getting a 5, well, that would be 1 out of 7. 1 out of 7 numbers are 5. Add those together. Once again, they're mutually exclusive, so add them together. I get 4 out of 7. So out of the 7 total outcomes, 4 of them are going to make me happy because they're either an even number, 2, 4, 6, or the number 5. Pretty simple, pretty easy to do. All right, what about the jar example? 20 marbles, 3 red, 7 blue, 10 green. What is the probability of selecting a red or a blue? Okay, well, once again, these are mutually exclusive. So it could be red or blue. They cannot be red and blue. It's impossible. So I think, okay, well, what's the probability I get a red one? Well, 3 out of 20 marbles are going to make me happy because they're red. Or 7 out of the 20 marbles are blue. So add those together. There are 10 total marbles that will make me happy because they're red or blue. None are both red and blue, so I can't worry about any overlap there. Out of 20. So I got a 50% chance of being red or blue, getting a red or blue marble. So that's pretty simple. But let's look at this example here. A spinner has 7 equally sized sections labeled 1, 2, 3, 4, 5, 6, 7. Same scenario we saw before. But this time I'm asking the probability of landing on an even or 6. Okay, now this one we got to be careful of. Even or 6. Now these two outcomes, even or 6, are mutually exclusive because they can occur, they're not mutually exclusive because they can occur at the same time. If I get a 6, it is simultaneously even. So these two events are mutually exclusive. So if I want to find the probability of getting an even number or a 6, let's see here. What's the probability of getting an even number? Well, 2, 4, 6, 3 outcomes out of 7 are going to make me happy because they're even. Or getting a 6. 1 out of 7 outcomes is getting a 6. But because they're not mutually exclusive, I got to do some extra thinking here. The number 6 got double counted. It got counted amongst the 3 even numbers. It got also counted here because it's 6. Well, if a 6 comes up, I'm going to be happy, but it shouldn't count twice. See, it got counted amongst the evens and amongst the fact that it's a 6. So I need to get rid of it. I'm not getting rid of it because I don't want it. I'm getting rid of it because I don't want to accidentally count it twice. Go back here, for example, when we talked about getting an even or 5. Those are not mutually exclusive. Okay? Or excuse me, they are mutually exclusive because they cannot occur at the same time. So I didn't have to worry about overlap. These 3 options, the 2, the 4, the 6, were different than this one option of a 5. There was no overlap there. But here, there's overlap. The 3 options that were even, 2, 4, and 6, and the option that's a 6 is right here. So they were both counted. I don't want the 6 to be double counted, so I have to subtract it away. So what's the probability of getting an even or a 6? Well, it is 3 out of 7. Think about that. right? Now you might be like, wait a minute, that's not how I would have thought about it, and that's okay, right? Maybe it makes more sense if you just said, okay, what's going to make me happy? Getting an even or getting a 6? 1, not happy. 2, okay, that's even, or it's a 6. 3, not happy. It's not even, nor it's not a 6. 4, okay, it's even, so that makes me happy. 5, it's not even, not 6, so that's not gonna me. 6, that makes me happy. It's even and it's a 6. Okay, great. It's both even and a 6. I don't care that it's both. I just care that it's going to make me happy. 7, not even, not 6. So 3 out of 7 numbers are going to make me happy. But you have to understand, if I walk through this slowly, here's the probability of getting an even, 3 out of 7. Here's the probability of getting a 6, 1 out of 7. But because the 6 is technically in both of those statements, even or 6, it's both of them, I have to subtract it away. Now, I know it's a little bit confusing, and again, I hope by the end of this video it's going to make a little bit more sense, but this is where the addition formula comes from. The addition formula is one of the most important formulas when it comes to probability. It says that the probability of A or B equals the probability of A plus the probability of B minus the probability of A and B. Now, when we subtract this away, we're not subtracting it away to get rid of it. We're subtracting it away so that it doesn't count twice. Because if they are not mutually exclusive, that means that some of this A might also have B. Some of this B might also have A. So if we add up A and B, we might be double counting the A and B. So we don't want that A and B to double count, so we subtract it away. Makes sense? Hopefully, if it doesn't, again, give me some time here. Now, if the two events are mutually exclusive, then we know that the probability of A and B equals 0. So in that case, we don't even have to worry about this back part. You ignore it because it's a 0 anyway, and you just focus on the fact that you add A and B together. Okay, easy. But once again, just consider the fact, are you mutually exclusive? It matters. It matters. Now, the last thing I want to leave you with is that the opposite of or, 1 minus the probability of A or B, is neither. If you find the probability of A or B, that includes A, that includes B, that might even include some overlap, A and B, but the one thing it does not include is neither. So the opposite of A or B is neither. Keep that in mind. All right, let's do a couple more examples so that this really kind of makes sense. I really want this to hit home. All right, back to rolling 2 die. If you roll 2 die, you add them together, add 2 die, add the sums, you can get a sum of 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, or 12. If you don't believe me, grab 2 die, roll them. One of those sums is going to happen. All right, what's the probability of getting a sum of 3 or a sum of 5? All right, now first off, these are mutually exclusive because you can't both be a sum of 3 and a sum of 5 at the same time. Can't happen. There is no overlap. So to find the probability of 3 or 5, all I have to do is find the probability of 3 and add the probability of 5. Easy. All right, I don't have to worry about any subtraction because the probability of 3 or 5 is 0. So I don't have to worry about it. I mean, I could write it if I want, but I don't have to worry about it because the probability of 3 and 5 is impossible. That cannot happen. All right, so how do I get a 3? Well, I could get a 1 on the first die, a 2 on the second die, or I could get a 2 on the first die and a 1 on the second die. Those are two distinctly different things. Either one of those is going to add up to a sum of 3. So that's 2 out of 36 total possibilities. Wait, what? Where did I get 36 from? Well, if you roll 2 die, you got 6 options on the first die, 1, 2, 3, 4, 5, 6. You got 6 options on the second die, 1, 2, 3, 4, 5, 6. So that's a grand total of 36 total different outcomes when you roll 2 die. And 2 of them are going to result in a sum of 3. What about a sum of 5? Well, to get a sum of 5, you could roll a 1 and a 4, or a 4 and a 1, or a 2 and a 3, or a 3 and a 2. So there are 4 out of 36 outcomes that result in a sum of 5. Easy. Add them together. 6 out of 36 is the grand total, reduces to 1/6. There's my probability of getting a 3 or a 5. All right, now if you're looking for one place for the question about or to make the most sense, it's probably in a two-way table. So here's a two-way table, 500 students. Some wear glasses, some don't. Some are freshmen, some are sophomores, some are juniors, some are seniors. What's the probability that I randomly pick a student who is a junior or wears glasses? Now here, I got to be concerned because there is some overlap. These are not mutually exclusive. There are 32 kids who are both juniors and wear glasses. There's 155 total juniors. Some wear glasses, some don't. 140 total kids wear glasses. Some are sophomores, some are juniors, some are seniors, some are freshmen. But 32 are both. So how do I find the probability? Well, I first got to find the probability of a student being a junior. Then I got to add the probability that a student wears glasses. Then I have to subtract away the probability that somebody is both a junior and wearing glasses. All right, so let's do this, and let me show you how easy this is. What's the probability a junior gets picked? Well, there's 155 juniors out of 500 that could get picked. That would make me happy. If any one of those juniors is picked, I'm going to be happy because I got a junior. Or, what's the probability somebody wears glasses? 142 kids successfully wear glasses out of 500. If any one of those kids is picked, I'm happy. But, excuse me, I got to be really careful because these 32 kids, they got counted here. They wore glasses. They got counted here. They were juniors. These 32 kids got double counted. They deserve to be counted, but not double counted. So I want to subtract away those 32 kids that were both juniors and wearing glasses. I'm not getting rid of them because I don't want them. I'm getting rid of them to stop them from being double counted. They were counted here amongst 155 juniors and here amongst 142 kids wearing glasses. So that's why I'm subtracting them away. So grab a calculator if you need to. 155 plus 142 minus the 32 leaves me with 265 out of 500. And if I want to get a decimal on that, it's 0.53, 53% chance, 53% probability that I reach in and I get a student who is a junior or they're wearing glasses. And I think that this is a great example where we actually see that idea of why we subtract the and away. Because you can literally see the 32 kids that got double counted. All right, we're going to skip that example. Sorry, I meant to skip it. Here is the last example. Probability that a family has ham for Thanksgiving is 18%. What does that mean? That means if we were to look at many houses, in the long run, 18% of all houses have ham on their table at Thanksgiving. 75% have turkey. So if we look at many houses, of all the houses we look at, 75% have turkey on their table. But guess what? Some have both. 11% of houses have both turkey and a ham sitting on their table. So here's the question. What's the probability we grab a random house throughout America and they have turkey or they have ham? Well, I'm just going to use the formula. I'm going to find the probability of turkey plus the probability of ham, and then I have to subtract away any overlap. Because why am I subtracting away the overlap? Why am I subtracting away the turkey and ham? Because some of these turkey people have ham. Some of these ham people have turkey. So if I'm counting, if I stop by just doing turkey plus ham, some houses are getting double counted. So it's really, really simple to do. 75% turkey plus 18% ham minus the 11% that have both. It's really, really is that easy. So 0.75 plus 0.18 minus 0.11 is 0.82. 82% of houses will have either turkey or ham. Now remember, or, I said this in the very beginning, or means one or the other or both. So in this case, when I say turkey or ham, I'm talking about turkey, or I'm talking about ham, or I'm talking about both. It's all together. When I subtract away the turkey and ham, I'm not subtracting it away to get rid of it. I'm stopping those houses from being double counted. Some of these houses have only turkey. Some of these houses have only ham, and some of them have both. That's what I'm looking for when we say or. Now, the opposite of or is neither. So if I do 1 minus 82%, I get 18%. And that tells me that 18% of people have neither. That means their table is absent of turkey and ham. No turkey, no ham, tofu, chicken, steak, who knows. But there's no turkey, there's no ham on it. Okay? So hopefully that makes sense. The big thing I want you to pay attention from this video is the addition formula, the addition rule. It's a really important rule. Make sure you understand it, and make sure you understand how it works and the difference between or and and. It's really important. All right, that's it.